Welcome to the Advanced Real Analysis series. Here we will rebuild integration, because apparently one perfectly good integral was not enough. This series assumes that you already know the basic ideas of limits, continuity, and differentiation. It also assumes familiarity with the one-variable Riemann integral, including upper and lower sums. If any of that still feels mysterious, finish the basic series first. Advanced analysis is much less charming when every sentence contains 3 unresolved mysteries. The Riemann integral divides the domain into small intervals and approximates the area with vertical rectangles. Make the partition finer, control the upper and lower sums, and hope they meet at the same number. For continuous functions on a closed interval, this works beautifully. The trouble begins when functions are discontinuous, unbounded, or obtained as limits of other functions. First, the proper Riemann integral on a closed interval is defined for bounded functions. But 1 over the square root of x is unbounded near 0 and still encloses finite area. The improper Riemann integral repairs this particular case by taking another limit. And the answer is 2. This is a mild defect because an improper integral patches it. The next defect is structural. Now take the characteristic function of the rational numbers on the interval from 0 to 1. The function equals 1 at every rational point and 0 at every irrational point. Every interval contains both rational and irrational numbers. Consequently, every lower sum is 0 and every upper sum is 1. No partition can close that gap, so this function is not Riemann integrable. Enumerate the rational numbers in the interval as q1, q2, q3, and so on. Define f indexed by n to be 1 on the first n rational points and 0 everywhere else. Each function is non-zero at only finitely many points. It is Riemann integrable, and its integral is 0. At a rational point, the value eventually becomes 1 forever. At an irrational point, it remains 0 forever. Therefore, these Riemann integrable functions converge pointwise to a function that is not Riemann integrable. The class of Riemann integrable functions is not closed under pointwise limits. A rather inconvenient feature for a subject built almost entirely from limits. Riemann integration organizes the domain into vertical slices. Lebesgue integration begins from a different direction. Group together points where the function has similar values. Very roughly, Riemann asks where the point lies, while Lebesgue first asks what value the function takes. We begin with simple functions, which take only finitely many values on measurable sets. Multiply each value by the measure of the set where it occurs, then add the results. More general non-negative functions are approximated from below by simple functions. Signed functions are then handled through their positive and negative parts. That description is deliberately rough. Before it becomes a definition, we need to say which sets are measurable and what their measures are. The rational numbers have measure 0, so their characteristic function is Lebesgue integrable with integral 0. Lebesgue integration cares about the size of the exceptional set, not merely the number of discontinuities. To define measure, we must first choose a collection of sets on which countable set operations behave properly. That collection is called a sigma algebra. It contains the whole space and is closed under complements and countable unions. In the next episode, we will define sigma algebras carefully, examine examples, and discover why ordinary collections of sets are not enough. Think of a sigma algebra as a bureaucratic filing system for subsets. Annoying at first, indispensable once the paperwork begins.